And thank you, Marin, for that great talk. I'm so happy to have followed your talk because you've really explained a lot of what I would just skim over. So perfect, thank you. Okay, so hi everyone. It's been such an interesting meeting. I've really enjoyed it. So big thanks to Dave Brain and the organizers for bringing us together. Today, I will very quickly tell you about measuring the magnetic fields of exoplanets using magnetic star-planet interactions, and specifically for hot Jupiter systems. Now, it feels to me like we've been doing this for a very long time, but the search for exoplanetary magnetic fields actually started a long time ago, and Marin already pointed out this 1986 paper by Wingley et al. But in fact, people have been proposing it for a decade even earlier. And the earliest reference I could find was from an internal memo from JPL from 1974, discussing the feasibility of detecting planets in the radio beyond our solar system. And I'm happy to send it to anyone who wants a PDF copy of it, because it's hard to find on the internet. But the reason why people have been looking and thinking about exoplanet hunting through the magnetic fields, as Marin said, is that Jupiter is the brightest radio source on in the night sky at about 20 or so megahertz. And because of that, it seemed like it would be a great planet hunting technique, in addition to discovering magnetic fields on these planets. However, we're employing a completely different method to search for magnetic fields, taking advantage of the fact that hot Jupiters orbit their stars within 10 or 20 stellar radii. So here is a 2-scale image of a fictitious hot Jupiter orbiting within 10 stellar radii around our sun. You can imagine that at these distances, all sorts of funky things are happening that are not happening in our solar system, but one of them is a magnetic interaction potentially between the planetary field and the stellar field. And this could manifest itself as increased stellar activity. So this is the mechanism that we will be using, looking for increased stellar activity phased with a planet's orbit. So you may be asking yourself, why doesn't this happen in our solar system? Well, first of all, we don't have hot Jupiters, and the Earth and Jupiter are just too far away. They're in this regime where the Alfvén Mach number, defined as the ratio between the wind speed from the star and the Alfvén speed, exceeds 1. But the hot Jupiters lie right here where it is below 1, something that I call the spy zone. So it's a perfect laboratory in which to look for these kinds of interactions. So long ago, just showing you some examples of the very first stellar spectra that we collected in order to look for this, is of the hot Jupiter host HD 179949. Here I'm showing on the left overlaid a bunch of spectra of the calcium-2 K line. This is a classic optical activity indicator in stars. And what you're seeing here is that night after night, the photospheric lines lie very nicely on top of one another, but this little tiny variability in the center, that is the chromospheric variation, indicating some stellar variability. And if you look at the residuals of these on the right-hand slide, you see a whopping signal. It looks whopping because these are extremely high signal-to-noise spectra, signal-to-noise of 500 per pixel, for those of you who care about such things. Now, the real thing that we need to understand is, why are these varying and on what periods? So it could be that it's just the star rotating, and that some sort of hotspot on the chromosphere is rotating in and out of view. However, it turns out that this modulation is in fact phased with the planet's orbit, not the stellar rotation period. And so this was our first detection of magnetic interactions for a hot Jupiter. We have multiple seasons that we observe this in from my group, and then a different group confirms it. And we do this with, this particular one again is calcium-2, but can be done with other activity indicators as well. So to show you the ones that we have thus far done this exact same experiment with, is this sample here, 17949, 189733. These are all kind of popular ones. Tau Boo, which Marin just also pointed out that there is a tentative LOFAR detection, and Upsilon Andromeda. And you might be wondering, these are all like the earliest, the first discoveries of hot Jupiter systems. This work is published by Wilson Colley and myself and collaborators in a couple of papers here, 2018 and 2019. So I refer you to those. But the key takeaway point is we see all this variability and it phases with a planet's orbit, not the stellar rotation. So now that we have measured, so if we say that the star-planet magnetic interaction, now we can measure the power emitted through this interaction, right? There are some models out there, and there's a whole bunch listed down below as well for other simulations that I refer you to and don't have time to discuss in detail. But if we can measure this, we know that it is related to the stellar magnetic field, which is measurable, the planetary magnetic field, which is what we want, and the relative velocity between the two, between the planet and the star at the location of the planet. Now, we do have, for all those four that I showed you, we have magnetic field strengths measured by Zeeman Doppler imaging. And then we can figure out what the magnetic field strength is at the location of the planet. And so we can pull out the magnetic field of the planet, which is amazing. And very exciting for us. And so here are the first four measurements of these four hot Jupiters that I already talked about, for which we have all the necessary information. And we're plotting our work, our measurements on the x-axis against the predictions by Yadav and Thorgren in 2017, where they predict magnetic fields of these same hot Jupiters using the internal heat flux scaling laws that we have seen already in this meeting, but they include the extra heat deposition from the star because these are hot Jupiters that are so close to their parent star. These ones that we've been measuring are about between 20 and 120 Gauss, which are a bit bigger than Jupiter's. And so one might think, well, why are they so big? And we're still trying to figure that out. It could be because of this, this extra heat deposition, certainly. But Marin already showed us these exciting results about looking at magnetic fields of substellar objects. And here's an example of some brown dwarfs detected by Melody Cow, and her collaborators. She's a Hubble Fellow in my group right now. And she and her collaborators have found very strong magnetic fields on brown dwarfs, as Marin already showed us. But one of them, serendipitously, happens to be a very young brown dwarf. And a young brown dwarf is, in fact, planetary mass. So this particular one is about 6 Jupiter masses. So what we're seeing now is there are planetary mass objects out there that have, at minimum, 2 kilogauss fields. And we haven't necessarily figured out why they are so strong. But then plotting our hot Jupiter measurements on this scaling law doesn't do too bad a job. So I think we certainly need to find more magnetic fields on these exoplanets, and we'll talk a little bit about that next. But I know that a theme that has come through this entire meeting is, well, what about habitable zone planets? And so this whole methodology of using magnetic star-planet interactions could work potentially for Earths around M-stars if the magnetic fields are strong enough. So here's a plot that you're probably very familiar with, showing how an Earth is in the habitable zone of a late star, late type star or low mass star. And it does seem to coincide with what I've been calling as the SPI zone, being within the Alfvén radius of the host star. Of course, there's lots of uncertainties of what the Alfvén radius of M stars actually are, but if it is around 10 stellar radii, then we could imagine doing this experiment with Earths around M stars. And it may even be a better way to do it, or not better, but a bit easier than even for the hot Jupiters, because the magnetic fields of the stars might be much stronger and the relative velocities could be much higher because of these very slowly rotating stars. And so it's possible that we would have greater sensitivity for the M-star planets. Of course, the M-stars are more active in teasing out the exact, teasing out the planet signal from the stellar signal will complicate things, but I don't think it's impossible. So we need to measure more magnetic fields, right? I think we all can agree on that in exoplanetary systems. And so I'll give a very brief introduction to one thing that I'm looking forward to in the future, and to get more of these magnetic SPI measurements. And that is a mission that we're working on to develop called UV scope. It stands for the ultraviolet spectroscopic characterization of planets and their environments. Now, the mission itself is designed to observe directly exoplanets through transmission spectroscopy in the ultraviolet, including the Lyman alpha transits that Ruth Marie Clay mentioned this morning, to do that for a large statistical sample. And so the mission is going to look at target 200 transiting exoplanets, both large and small. But there will be a sample there where we will intrinsically have collected lots of stellar activity measurements just by virtue of trying to do the other experiments that the mission is planning on doing. We're developing this for this upcoming mid-X call, and the output data, just to show you, will look something like this. 2 minutes, thank you. Will look something like this, where we have a 60 centimeter telescope that feeds a 2-armed spectrograph. We will have a high resolution or medium resolution far UV channel and simultaneously collect low resolution NUV data. And so we will have lots of these beautiful activity indicators in stars of lots of transiting exoplanetary systems. So we will both simultaneously be studying the planet and its atmosphere, but also the stellar environment of those planets, and maybe be able to tease out some more of these SPI signals. So, so there are more exoplanet detections coming, right? I think we're just getting going. So we could have more of these monitoring techniques, like I just said, with UV scope and with other perhaps small sats at high energies. We do have another calcium-2 detection that we just need to confirm. We have a very nice new detection with optical spectroscopy, but it needs a little bit more confirmation before we're ready to publish it. There's a proposed mechanism through spectropolarimetry of the helium 10830 line that is out there in the literature. Marin already talked very nicely about ground-based observations, including LOFAR and the Owens Valley Array. The small sats, the radio small sats is one of them. The Sunrise being a Pathfinder mission for that's going to look at the sun with a cluster, an array or constellation of radio observations, but we'll be learning a lot technologically and scientifically from that. And lastly, of course, the lunar-based array Farside that we heard from Jim Green this morning a bit about, and also from Marin. So we're really on the cusp of all of this. So following instructions, David Brain said in our email that we should end off with one big question that for discussion now or later offline. And the one that I propose that came up also, Ulfar asked it just in the last talk, is how do we disentangle magnetic star-planet interactions from stellar activity or non-magnetic aurorae, both in the radio and in the optical, and however we're going to do it. So we're going to learn so much about stellar physics. I'm very excited about that component as we try to answer this question. All right, I'm done. Thank you.
Thank you. Is there any questions? Feel free to raise your hand or post in the chat box. A question from Dave Brain. To what extent do you think the Io-Jupiter interaction provides an analog for SPI? What is that interaction missing?
Sorry, can you say that again? I just saw so many comments here.
Sorry. To what extent do you think the Io-Jupiter interaction provides an analog for SPI? What is that interaction missing?
Yes, so that does provide it. One of the very first models of SPI that came out after our first paper in 2003 was by Ipedal in 2004 that uses the unipolar inductor models of the Io-Jupiter system. And so I refer you to that paper to look at the details, but there's certainly at least geometric lessons that we can take from there when you think about the hotspot. If you guys know that classic image of the HST image by Clark et al., where you have the hotspot of the aurorae on Jupiter that is modulated by the orbit of Io. So it's definitely a great starting point.